Alright, now to write electron configurations. When we looked at quantum numbers, we were describing the location, sort of like a street address for one electron. When we're writing out the electron configuration for an atom, we're more interested in getting a street address for every atom, now, or for every electron rather. Now, if you stop and think about what it would be like to write the set of quantum numbers for every single electron in an atom, that could be extremely painful. And let me share with you why. This is the periodic table of the elements, and notice these big numbers right above the symbol, like 22 for titanium, 20 for calcium, so on and so forth. That number, which is called the atomic number, lets you in on, amongst other things, how many electrons the neutral atom will have. So for instance, calcium has 20 electrons, titanium has 22. If we look at calcium, if we write the quantum number for every electron in there, well, it's 20 electrons at 4 quantum numbers each. That means we're writing 80 total figures. That could get ugly fast. So what we do is we write a shorthand version of this where we're mostly interested in the energy level and what sub-level things are in. So let's start with a very, very simple one. Let's start with, well, hydrogen. So we're going to write an electron configuration for hydrogen. Now the way we do this, I've just wrote the symbol for hydrogen and then put a colon there, and we're going to write on configuration afterwards. So this is just saying hydrogen, wait for it, something different's happening, and then we're going to write this out. What we need to do is we need to first figure out what energy level the electron is going to end up in, and then what sublevel. And to do the Aufbau principle, so that's AUFBAU principle. And what is that? Electrons will occupy the energy level that is closest to the nucleus first. And within an energy level, they'll occupy the sublevel closest to the nucleus first. So the energy level closest to the nucleus is the first energy level. So what we do is we write a big 1 that tells us we're looking at the first energy level. And then we think about the sublevels that are in the first energy level. Well, there's only one. That sublevel is S. So we say that we're looking at the 1s sublevel. And next thing we want to do is think about how many electrons are going to be in that 1s sublevel. Well, hydrogen just has one electron, just 1. And we write that 1 as a superscript. So what this tells us is that hydrogen has one electron and it's in the first energy sublevel. So let's go on and make this more complicated, and now let's do it for helium. So the first place that will fill up is the 1s sublevel. And now helium, if we look, has 2 electrons. And since an s sublevel can hold 2 electrons, there they go. Alright, easy so far, right? Let's look at lithium, and it adds a little bit of a wrinkle for us. For lithium, just as always, the 1s sublevel fills up first. We can put 2 electrons in there. And what happens is that we have 3 total electrons. So the first 2 go there, and then the next electron has to go in the next available spot. Well, the first energy level only has an s sublevel. Next available spot is actually the second energy level. And in the second energy level, the lowest energy sublevel is S, so that 1 remaining electron goes in there. So now you can see we have all 3 electrons accounted for, 2 there and 1 there, and we've said exactly where they are. 2 of them are in the 1s. Alright, so that's all 3 electrons there accounted for. Let's step this up a notch. Let's do oxygen. You can see oxygen has 8 electrons. So just as before, the 1s sublevel fills up first. We can put 2 in there. Next up is the 2s sublevel. We can put 2 electrons in there, so that's 4. After 2s, though, we need the next lowest energy level 1, and that would be 2p. Now we need 8 electrons total. We've already used up 4. The p sublevel can hold 6, but we've only got 4 electrons to put in there, so we say 2p4. And again, this just tells us where everything is. So in oxygen, we have 2 in the 1s sublevel, 2 in the 2s sublevel, and then 4 in the 2p sublevel. Alright, this is going good so far. Let's now look at where this starts breaking down and getting crazy. And to do that, let's take, let's do something fun here. Let's do bromine. Ah, no, we did bromine in class. Let's do arsenic. Arsenic, do not eat this at home. All right, so for arsenic, we should have 33, count them, electrons. Oh boy, oh boy. So let's go through. We have the 1s sublevel fills up, 2s will fill up, 2p will fill up. Now we've used a total of 10 electrons. Now, after 2p, we have to remember that the second energy level only has an s sublevel and a p sublevel. So the next place we go is the 3s sublevel. The third energy level is the next lowest, and then s is the lowest sublevel within that. And then 3p6, and here is where the wheels fall off, because we would assume that the next lowest one would be the 3d sublevel, and we would actually be incorrect in assuming that. The reason being is that once you get into the higher energy levels, and I'm going to draw a diagram over here, those energy levels start to overlap. So, see if I can draw this small enough to get everything in there. We have the 1s sublevel, and then next up in energy we have the 2s sublevel and the 2p sublevel. So if we think of this as the energy level, and there's that energy level. Oh, excuse me, shouldn't have drawn those up there, but you get the idea that 1s and then the 2s doesn't overlap for that. It starts right where it ends. Same thing with 2p. 3s picks up right where that left off, and then there's 3p, and then there's 3d. So this is like the third energy level. The fourth energy level, though, actually starts down here. 4s is closer to the nucleus than 3d, which means that as these start to fill up, the next thing that fills up after the 3p6 is actually the 4s sublevel. So 4s2, and then the 3d sublevel, and I didn't leave myself enough room here. So the 4s sublevel represented here, and then the 3d sublevel, and then we get to 4p. And if we're counting carefully, boy, I didn't leave myself enough room there. If we're counting carefully, we should have 3 electrons left. And so for arsenic, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. The 4s comes before the 3d, then 3d10, and then the 4p sublevel. All right, now let's make this really super complicated, and let's do gold. AU, and this one will take us a while. So for gold, we're going to need 80 electrons. So here we go. The 1s2, 2s2, so we got 2 electrons there, 2p6, that's going to fill up next, 3s2, 3p6, and then just like we talked about, the 4s sublevel is actually closer to the nucleus than 3d, and this will always happen rather, that the s sublevel, once we get to this point, always fills up before the d sublevel. So when we go to fill up the 4d sublevel, the 5s sublevel will actually fill up first. So 3s2, 3p6, 4s2, 3d10, 4p6. Let's stop there and get a count. If I'm not mistaken, that should give us 36 electrons there. We've got a ways to go. All right, after 4p, we would think that 4d fills up next, but then we have to remember that the s sublevel fills up first. So we have, or the 5s sublevel rather. So 5s2. Now we have 4d10. And now it gets confusing again, because after 4d, the next available sublevel in energy level 4 would be the f sublevel. But just like the d sublevel doesn't fill up until later, the f sublevel doesn't fill up until much later. And let's see if I can draw this in here. I'll really have to cram this up tight. I didn't leave myself enough room. So fourth energy level has all of those. We know the 5s will fill up first. The 5p sublevel will actually fill up before the 4f. And to make matters even worse, the 6s sublevel will actually fill up before the 4f sublevel as well. Which means as we get higher and higher up away from the nucleus, these overlap significantly. So from 4D, we're actually going to go to 5p, and then from 5p to 6s, so 6s2, and then from 6s we go to 4f. So notice what a mess this is. 4 is spread out with these significant things between it. So between the 4p, or the 4s and the 4p, you get 3d. Between 4p and 4d, you get the 5s. And then between 4d and 4f, you've got 5p and 6s. My oh my. I'll show you an easier way to keep track of this in just a second. So after we have 4f, the next thing that fills up is 5d. Oh my goodness. And then with the 5d, whoa, hold your horses there. With 5d, we're not going to fill that up entirely. If we count this up, we should have 9 spots remaining, so that would be 5d9. And hopefully if we count these up, that actually will equal 80. I won't go through the pain of making us do that. But if you count up these numbers along the top, it should add up to 80, and that would be our electron configuration for gold. Now, I promised you an easier way to look at this, and it would be shameful of me not to show you an easier way to do this, because you don't have to just straight up memorize these. The periodic table has done that for you, and it is quite nifty, for lack of a better term. Notice that in this column right here, this spot that's higher, there are 2, count them, 2 elements in each. Let's keep that in the back of your mind. Over here, for this raised part, 1, 2, 3, 4, 5, 6. Here in the middle, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And down at the bottom, 1, 2, 3, well, we'll talk about that in a second. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. For those of you playing along at home, this column here has the same number of spots in it as there are electrons in the S sublevel. This corresponds to the P sublevel, D sublevel, and F sublevel. And you can actually predict what's coming next by just following these atomic numbers, the numbers over there. So we start, well, I should say this too. Notice we talked about 7 energy levels. And there are 7 rows on the periodic table. Those are called periods. So this would be a period going across. To find out where you're going, start with hydrogen, and you're in the first energy level because you're in the first row, and this starts in S. So there's 1s1, 1s2. You can think of helium as being split over here for these purposes. And then once 1s is filled up, we're going to 3. Now we go 2, and we're in the S area. So 2s is the next thing to fill up. So follow the numbers, 3, 4, 5. So once 1s is filled up and 2s is filled up, the next place we go is 2p. And then you follow those numbers, 10, next it goes to 11. So after 2p, we go to 3s. After 3s, we go to 3p. Follow the numbers, 18 to 19. After 3p, we go to 4s. And now there's something you have to remember about this. For the D sublevel, what happens is that even though this is in the 4th period, the 4th row of the periodic table, it goes with the 3rd one. So for everything in the D sublevel, it's pushed down 1 from where it would otherwise be. So whereas this would go with 3, it's actually with 4. So we have 4s and then 3d, and then after 3d you go to 4p, 5s, 4d, because it's in the D, you have to take 1 away from whatever row it's in. Now, to make it even more confusing, with F down here, take whatever row it's in and subtract 2 from it, whereas D, you took away 1, here you got to take away 2, and these start right over here. Not sure, there's different opinions on this, but they drew this coming out of here. But what happens is that going from the 6th, or the 6s energy level, we now go into here, and you can think of lanthanum and actinium as being down here. So these are part of the F block, and this last one over here is actually part of the D block. So from 6s, you actually go into 4f, and then back to 5d, 6p, 7s, 5f, 6d, and so on and so forth. So the periodic table actually has your back in writing these electron configurations quite quickly. Practice, practice, practice. There is no substitute for practicing this. Do these until your arm falls off, switch to your other hand and do them some more. Make sure that you know exactly how to do this. It's easy points on the test. Good luck.